I start. Yeah, I have
This is you're taking the real part. So
You starting on this board then?
Yeah, let's give that a go. Let me slide in this real quick. Sweet. Get it started. Hey everyone, y'all ready? Y'all here for the TA review? Everyone's stuck. Everyone's excited. Okay, you can bring your chairs in a little bit. I think we got a lot of people, so like try and squeeze in as close as you can. That way we don't have to yell. You want to find this? Let's see. Hopefully everyone on Zoom can hear us.
Yeah.
Say thumbs up if you can hear us.
No one has a camera on, so I have no idea.
Oh, we got a thumbs up. See?
Oh, okay, there we go.
The magnitude of A
So, okay. Let's see. Like, yeah.
Settle down for a quick second. All right, let's kick off this TA review real quick.
Everyone get out your chapter summaries. That'll be step number one for sure. Make sure you got your chapter summaries because we will be referencing these a bunch, telling you things that are going to be important, the cool things. For this exam, this test is just going to be about like heat, right? It's going to be about, I mean, it's been 2 weeks, but we've learned so much. It's been crazy. So we've got like heat, we have expansion, you've got engines, we have what, like, I'm trying to think. Entropy,
Power, energy.
So we're going to go over a lot, but we're going to focus in on equations that are important to use and where they are in your chapter summaries. But yeah, we can just give it a start.
Yeah. So the first thing we're gonna start off with is the basic temperature stuff. That's something you should always know. You should know how to convert Celsius to Kelvin. If you want to speed it up, any parts where you think you might be using that equation, you can just write that in your booklet. But this should be something ideally you just know off the top of your head, so you're not spending time stressing about finding it.
Yeah. And my advice is if you're ever worrying about should I change it into Kelvin or not, just do it. Just change it into Kelvin. That way, worst case scenario, you just convert it back into Celsius at the end. But yeah.
Yeah, keeping it in Kelvin has never hurt anybody. Keeping it in Celsius, just a general rule, is you're only going to want it in Celsius if you're calculating the difference in two temperatures, because that won't change either way. But if you're not sure, Kelvin's always the way to go.
Yeah. And so then moving on, we did a couple questions with like linear expansion and these things where, you know, like if you heat up an object, it's going to expand. And so in your chapter summaries, you should highlight or underline that equation. It should be on the next page or so. And the equation I think it gives you is just for alpha. So it's just for that coefficient of expansion. If you want, you could write down, you know, solve for the length final. That's convenient to have in your chapter summaries. Whatever you write down, you can have, so it's beast. But just remember that this is going to be an important equation.
Yeah. So length final, yeah, I just write that in your expansion area, like of your notebook. That'll be a good one to have handy, so you're not trying to derive it on the fly.
Yeah, that's just the next coefficient expansion.
Yeah. From there we go to ideal gas laws again with the Kelvin. Ideal gas law does not work if temperature is not in Kelvin. If you leave that in Celsius, you will get a random number, and Professor Allred might just put that number on there, because it's a very common mistake to make. So just because you get an answer won't mean that it's necessarily correct. You could have also made the common mistake.
Yeah. So make sure Kelvin is your friend.
Yeah. R also equals 8.314 for all ideal gases. That's one you want written in big bold letters so you're not scrambling looking for it. It should be in the beginning of your book towards the constants section, but just writing it down near any equation that uses it might save you a little bit of time.
Yeah. And one thing that's important to remember is the difference between like specific heat and latent heat. So when we're working with like processes, calorimetry and stuff like that, when we have ice that's heating up, melting, and then heating up a little bit more, it's going to go through different processes, right? And there's different amounts of energy that it takes to transfer through each of those stages. And so whenever you're working with specific heat, that's going to be your temperature is changing. So that's why in the equation you have this change in temperature. So like let's say you have a negative 15 degrees Celsius ice cube that's heating up to 0. You can know, okay, that's a change in temperature. I'm going to be using my specific heat, and you're going to want to use the right specific heat. What is this called? The it's the N, right? Or it's C.
No,
It's your C. It's your specific heat constant. And remember, ice is different than water. They're different. I made that mistake on the test.
Not the same. Yeah, what's up?
So when you're doing like a calorimetry problem, you have your term like ml. How do you know if it's supposed to be positive or negative? I feel like it's been
Yeah. So the way I like to think about it is if the water is freezing, you have to slow down the particles so that they can turn into the solid, right? And so that energy is being released back into the system, which means it's negative. So that means that the amount of energy it costs is decreasing because energy is being put back to the system. Whereas if you are melting something, you're having to put more energy into that substance in order to free up those bonds to turn it back into a liquid or to go from a vapor to a liquid, etc.
So freezing is negative, thawing is positive.
Yes.
And that's over here on latent heat, right? It's going to be traveling through. I mean, we learned about this in chemistry. There's no change in temperature as it's changing phases. And so this one's really easy, nice and handy. Also very different numbers. They're a lot bigger. Yeah.
Will we be given any latent heats or things like that on the test, or there wasn't?
The water ones would be good to write down. Anything else, I don't expect you to have to memorize. Another big thing about that, if you are given those values, make sure they're in joules per kilogram. Because a lot of times, even in textbooks and just on scientific tables, it'll be given in kilojoules per kilogram because it's just a much neater number than because you can either have like 3.33 times 10 to the fifth, or you can include all those zeros. So a lot of the times it will be in kilojoules. So make sure to convert that if that's the case. Don't just plug it in without checking first what units you have.
Right. What units is that again?
You're gonna want it in joules per kilogram.
And if it's your specific heat, it's joules per kilogram degree Kelvin.
Degree Kelvin or Celsius, and that won't change what temperature you use because using it in that way, it doesn't matter if it's Celsius or Kelvin. Yeah, because that's referring to change in temperature.
Right. And so one thing that you have to remember is when you're doing these, making each thing equal, when you're doing calorimetry, is you're going to have Q cold plus Q hot equals 0. Where you're saying the energy of this one plus the energy of the other is going to equal out in the end. And so you set Q cold equal to negative Q hot because it'll end up being the opposite. So you have to remember negative or else your signs get all mixed up and you have a huge mess. So just make sure Q cold or Q of the lower substance, one substance equals Q or negative Q of the other substance.
Yeah, essentially if the colder substance is gaining energy, that is because the hotter substance is losing energy.
So those will
Yeah. So the energy gained by the cold substance will be equal to the energy lost by the hotter substance.
Sweet. Any last questions before we move over to energy?
Yeah, that'll be it for calorimetry, except we'll be going over like an example over an engines that works with both engines and calorimetry. So we'll have an example problem if that's what's needed. But after that is energy. Oh joy! Don't we all just love energy?
It's the best. So flipping over, we're in chapter 20 now in your chapter summaries, I think. My pages are numbered different. If some, what page is it on? 17, page 17. Oh, I lied. But yeah, no, we are good. Yeah, we're good, yeah. Or yeah, because it kind of touches on work, and then we go to the next
And then it
page.
goes like 23.
Yeah. Okay. So, yeah, go for it.
All right, so one very important equation is going to be this one. Energy internal is equal to moles times the specific value, constant volume, times temperature. So the reason that this equation is important is because what this equation tells us is the internal energy of an ideal gas is dependent solely on its temperature. Its temperature and whether or not it's monatomic, diatomic, etc. So this is the only equation you're going to be using for internal energy of an ideal gas, essentially.
Exactly. It's pretty easy, really simple. Sometimes it's easy to overthink that one. But if you ever are asked, what is the internal energy of this substance? You should be able to figure it out. So like sometimes they'll ask you like, here's a gas. Its temperature doesn't change at all. What's the change in internal energy? You can know. 0, right? Yeah. So
with this as well, if you're not given moles or temperature, you can find these values using the PV equals nRT equation. Because sometimes you'll be given separate values, which you can plug in and replace that N and that T.
So now we're doing it with.
So writing that, yeah.
And this CV, that's more for like monatomic, diatomic gases.
Yeah.
exactly.
So is this only for, I guess, gases?
Yeah.
It's ideal gas.
It's like for ideal gases specifically.
Which we only work with ideal gases. You're never gonna get like a weird.
Not in this class.
Yeah.
Thermodynamics, the class a little different. This is going over everything in its idealized state, saying we wish this is how things work. So it makes it a lot easier.
And so kind of moving on with this energy stuff, there's a couple different ways to change an ideal gas, right? You can compress it adiabatically, isothermically, isovolumetrically. What's the last one?
Isothermal.
Yeah, isothermal. So there's all these different ways to compress a gas, which are going to follow one of these curves. And so in each of those different scenarios, the relationship between energy and work is different and heat. And so in your chapter summaries, it would be a good idea to write down next to each of these scenarios, adiabatic, isobaric. Each of these graphs is useful. And then these ways that heat and energy are related to each other.
Yeah, and these graphs will be up afterwards. We're gonna keep this here for a day or two, so you can come up and write them down and draw them. Pretty useful, and they all have like their own specific process. Those are outlined in your chapter summaries in the book. So just highlighting those in case there's conceptual questions would be a pretty good idea. Like knowing adiabatic means that there is no heat change in the system. That's just like something you should be able to have highlighted or written down that you're like, if it says, hey, there's no heat in this problem, then you go, okay, so this is an adiabatic problem, so I can assume there's no heat. So the entire change in energy is related to work.
Yeah. And so like taking that into not like if we know that there's no heat, if we know there's no heat, then any internal energy is going to equal the work done on the system. Yeah.
On the graph.
Yeah, it should be V. It should be V.
Oh yeah, they should all be.
They are all V. And then that was your other question too?
Yeah.
Perfect.
Okay.
There you go.
Sorry about that. All right. There we go. So these equations are very important. The pressure times volume to the gamma is equal to pressure initial times volume initial to the gamma. So these equations you'll have in your book, and they're fairly self-explanatory. You definitely don't want to highlight how to get gamma, which is in your book, or write it down next to them if you want, which is just CP over CV. Something that's important to note is this also can be affected by PV equals nRT, which means that you can get this equation, which allows you to relate pressure and temperature in an adiabatic equation, where it's pressure to the 1 minus gamma times temperature to the gamma is equal to the same thing, is equal to constant. So that's a good one to know because you might be only given pressure and temperature in adiabatic equation and not told the rest of the information. And that again is derived from PV equals nRT.
Any questions about that little section? And we can take questions at the end, just for a
Yeah.
second too.
We should have a little bit of time left over at the very end for questions that are like more general or even more specific, depending on what you need. Another good thing to note, you have Q equals NCP change of T and Q equals NCV change of T. The difference between you when you use those is CP, the one that has CP is for constant pressure problems. The one that has CV is ones for with constant volume. Let me make sure. Yep, I did do that right. Yep. CP, constant pressure, CV, constant volume. And that applies specifically to these equations. If you do the other way and accidentally put in a CV for a problem with just constant pressure, you'll get an incorrect
We don't like incorrect numbers.
number.
So yeah, there may be a question on the exam where it shows like a graph like this of a certain gas where you have your pressure and your volume and you have these isothermal curves. And so basically what that means is like if you travel along this curve, you're gonna have the same temperature the entire time, right? You can have this volume and this pressure and it'll be the same temperature as this volume and this pressure. And what you might be tested on is these movements from one to the other. And so that's going to just fall into one of these. It's like isobaric, it'll look like it's just straight across. Isovolumetric is going to be straight down. Isothermal is going to follow one of the curves, and adiabatic is going to just be a little bit steeper than an isothermal curve. Does that make sense?
Yeah, again, those graphs will be up for a while. So if you want to come up, draw them down, that would be a very good idea. Because, I mean, I took this class a while ago, but I definitely remember a question or two being just purely related to those graphs. But we also haven't even seen the new exam yet. So.
That's true. I have no idea.
So this is all speculation, but I'd bet good money that that's all there somewhere.
We can hit, so root mean squared. There was like a question on one of the homeworks about that. It's simple concept, but you just have to know it, right? It basically just means you're going to take up all your values, square them, divide by the total number of values, and then square root that. It's just a fancier way of taking an average value. That's a little bit more. It's better for when we're working with temperatures, because there's like a whole rabbit hole with like kinetic energy having a value squared. And so it's better to square your values and then find the square root of that. But just know that's what root mean squared is and how to solve for it.
And then something that I've noticed a lot of people don't fully understand conceptually is the relation of energy, work, and power. So I have it written here. Essentially, energy is obviously what it is. It's energy. Energy over time is work. And then energy over time squared, otherwise known as work over time, is equal to power. So that is how they relate. Energy over seconds is equal to work. Work over seconds is equal to power, or energy per second squared. It's similar to the relationship of distance, velocity, and acceleration.
So we've got the formula of energy equals work plus Q.
Yes.
And there's no in there. Would it not be energy equals work over time?
So,
Because
energy's in joules.
Yeah.
Work is also in joules.
Yeah.
So why are we fighting for seconds?
I believe it's because
So I feel like, so there's like two different ways of thinking about work being done, right?
Yeah.
One way you can solve for it is force over a distance, right? Force times distance.
Yeah.
And so with gases, you can, if you're like squishing a gas down, if I'm the guy doing the work, then I'm doing positive work on the gas because my force is moving a positive distance.
Yeah.
The gas would be doing negative work, right? Because it's getting squished down. It's pushing out, but it's moving a negative distance. So it's doing negative work. So that's kind of,
This is just one of the ways to refer to work as. There is multiple equations for what work is, and they're all essentially the function of the same thing. There's just different ways to put it. But yeah, for this particular case, like this is referring to rate. Because I remember there was one of the questions on the homework asking for rate in, I believe it was in the heat engines area. And it was like, what is the rate of work? And so that's the rate of work is power.
Right.
Rate of energy is work. And so just that general connection.
yeah.
That when you say rate of energy, it means work. When you say rate of work, it means power.
Cool. Yeah. I think we should be good for that part. There was a question in the homework about a kettle boiling water, and it was like it's 100 degrees on this water. It's getting boiled off at a certain rate, you know, like so many kilograms per minute. Yeah, we worked on this one together.
We struggled on that one.
It's a tough one because you have to make that connection between power is work per second, and you can find like the work being done. It's just like all like went together, but it's just remember power is this work per second.
Yeah.
So yeah. We can move to engines real quick. Yeah.
I don't know how much of this board they're actually seeing, but it's better than nothing. Yeah, okay, that's good.
Okay.
So first part of engines to understand is from a conceptual standpoint, it's a little ways in there, but I want people to understand it before we go into the rest, because I know a lot of people are confused. What makes the Carnot cycle special? So what the Carnot cycle is essentially you are getting the maximum efficiency possible according to modern physics. So the reason, what you'll mainly be using it for is you'll be using it to find the coefficient of performance or the efficiency of the engine. The reason that it's not the same every time is because depending on the temperature difference between the intake and what you are heating or cooling, there's a maximum efficiency possible. Because like efficiency is not always going to be the same. It depends on the difference between the two substances. Because the closer a substance is together, like you can be much more efficient getting something from 99 degrees to use to cool to heat something at 98 degrees rather than going, this is at 100 degrees, this is at 2 degrees, and we're going to heat it. You have a much different ratio of efficiency. And that's what that represents, is the maximum possible efficiency you could get with the difference in the temperatures you're using.
So Carnot engine is kind of impossible in real life, but we like to use it because we can understand how efficient our other engines are based off of like the Carnot engine. But for your test, basically, you're just gonna have to like remember that the Carnot engine works a little bit differently than the other engines because it's idealized.
Yeah.
You should be told that you're working with the Carnot engine. And so just understand Carnot engine, we're gonna be using these equations over here. If it's a different type of engine, you're gonna have to solve for heat and use these equations on the left side.
And the other option for that kind of problem that could relate to the Carnot cycle is it might just give you some values and say, hey, we want to do this at maximum efficiency. What value would we get? And that means that you would be calculating your coefficient of performance from the Carnot cycle.
Yeah.
So just know if they want best efficiency, that's what you're pulling from.
Does anyone have any questions on heat engines, refrigerators, kind of how they work? One thing that I just thought of is heat pumps or like refrigerators are opposite of engines. And So that's why everything's flipped up and around. The way I think about it is like a refrigerator. You put work into a refrigerator to get a heat flow. And then engines, there is a heat flow that causes work to come out. So that's like the conceptual side of it.
Is there, in terms of the equations and the problems that we've done, is there any practical difference between a refrigerator and a heat pump? I know there is one actually, but like.
Right. So I know a refrigerator is like one type of heat pump. It's going from it's taking heat out of a cold area. Because you could have another heat pump where it's putting heat into a cold area. And so a refrigerator is just like a type of heat pump that has one sign going one way, but they're basically the same.
Yeah, essentially a refrigerator is just a heat pump made for cooling.
Yeah.
So that's the only real difference. Like other constructions generally differ between cooling and heating because you don't just have a switch that says put it in reverse. But for all intents and purposes, we pretty much consider them to be the same thing. It just identifies whether you're heating or cooling a substance.
Yeah.
That makes sense. In class, you drew a diagram where there were like arrows describing the cycle of a heat pump.
Yes.
And you said that we would.
Okay.
In which direction it needs to be going.
Yeah, that is true.
That's one.
That's this guy, right?
Yeah.
Let's see. Let me try and remember. Okay. Yeah. So when working with an engine, luckily I have it written down. You have arrows going like this. In that direction. The shape isn't, it could be a perfect square. That would be if you're doing like an isovolumetric process, an isobaric process down. Engines don't do that perfectly, and so it might be like a little skewed, but you'll be moving this way for an engine. This is an engine. And then you'll be going the other way for a heat pump.
For both cooling and heating?
Yes.
Yeah. Essentially, this is just running it in a loop of cooling and heating.
Why is that? Why is it that they have to go in one direction for one and the other direction for the other?
It's because when you find the area under a curve, that is the work that is being happened on by this thing. And so, because when you follow it one way, the work is, there's like negative work going this way and then a bigger positive work going this way. And so this engine has a temperature gradient that's falling and then going back up. And so because of that, you have more positive work than there's negative work being done. And so that's how it's able to like do work. But then when you go the other way, there's more negative work because the gas, you have to put work in basically for this temperature gradient to change. If that makes sense. Does that make sense?
Are we saying that heat pump does negative work?
Let me think. Heat pump does negative work.
You put work into it.
Right, you put work into it,
Right.
and then it's
Yeah.
going to cause the temperature, the heat to be moved. So I'm doing positive work on it, it's doing negative work.
Yeah.
Temperature gradient is created.
It's like equal and opposite reactions. In order to put work into the system, work has to be put into the out. That's what like exhaust is. That's why a refrigerator cools the inside, but if you ever touch the back of a refrigerator, it's actually hot because heat is radiating off of it.
And so then that would be, the radiation part of it would be this part, right? Because you're radiating heat to get back to this side, and then this would be, you expand the gas, and then it sucks up a bunch of heat, and then you compress it, and then you can radiate all that heat. So that's how a refrigerator works. And then an engine is the other way. You say, okay, I have some gas. It's sitting here. It's gonna expel. Well, no, this would be, it's heating up. You heat up the gas, you compress it, it cools down, and then it expands, and then it would be able to pump out work.
Yeah.
Yeah.
So in the equation E equals 1 minus QC over QH, is the E like, is the E the internal energy or what is it?
For
Ask that again. Sorry.
oh, this right here.
Yeah.
This is efficiency.
Efficiency. Yeah.
Yeah.
Different E.
Different E's, lots of E's, all the E's. Looks like, let's say,
So, yeah, so the Zoom meeting is gonna end because I don't have Bougie Zoom. If you want, send in the chat. If anyone wants to have me send out another link, I could just start another Zoom meeting. Just let me know. But honestly, for the most part, all that we have left is entropy, which you all learned about recently. So we could go over that real quick, but that's for the most part, everything that's gonna be on the test, all the equations that you have to remember. And you've already taken one of his tests before. And so you already know that you're not going to see the perfect equation on these tests. You're going to have a little bit of ingenuity, read the problem, know how to apply these equations. But that's going to come from just all this homework that you've been doing, all the practice you have with these equations. So before we hit entropy real quick, just my final bit of advice would be look over the homework again and make sure you can kind of see ways you can use equations in different ways. And that'll be helpful on this test.
yeah. Also, especially even including entropy, we're gonna do some examples with it. But whenever you're doing problems that are related to specifically engines or entropy, stuff like that, don't forget about the older equations because there is a lot of throwbacks to previous equations. And like the first example or second example we're gonna do specifically covers an example of that. It's gonna cover the water being put into a fridge and calculating how much work needs to be done until it's frozen. So that's gonna be related to that. But now I guess we'll do entropy real quick and then we'll do some examples and answer more questions that people have. So for entropy, something that I have noticed a lot of people struggle with the equations is the last equation in there. It's pretty far back. The NCV ln T over T naught plus NR ln V over V naught. That one. Something to keep in mind there is if you're given an equation with constant pressure, for all of you who haven't been to the TA lab today, the homework due on entropy uses this specific principle. So you're going to have to use, where's the, is PV equals nRT. So PV equals nRT. For this case, we're saying pressure is constant because that was the variable set, one of the problems, and it's a pretty common thing to have in a question set, say at constant pressure, we're doing something. What you can do is you have V over T is equal to N, that is not N, NR over P. These values are all constants, which means that you can set volume initial over temperature initial equal to volume final over temperature final. From there, you get volume initial over volume final is going to be equal to temperature initial over temperature final. So what that means is for your equation related to NCV ln T over T naught plus NR natural log of V over V naught, you can solve for either temperature or volume and plug in that ratio for both. So if you're able to solve, if you're given temperature initial or volume initial and are able to solve for the final of either, that ratio will give you the answer for both of those variables you're putting in, the T over T naught and V over V naught.
So that's just an example of, although we're in entropy, we're doing a throwback to ideal gas law. You're gonna have to know how to use equations with each other.
PV equals nRT should always be on your mind. If you're wondering, if you are given variables and you're not sure how to get the variables you need for the equation, the first thing you should check is what is constant in my PV equals nRT and what can I set that constant equal to?
So when do we know, just to use the V over V equals T over T versus this, where we've got the same thing, V over V equals T over T, but with the gamma minus one? Is it just when they give us a, say, it's monochrome, and we're like, oh, we better use gamma minus one?
So this is specifically for adiabatic questions, which means that no heat the heat in the system doesn't change. No heat is being added, no heat is being removed. Typically, you'll be told that it's adiabatic, but just also keep an eye out for the phrase no heat. If no heat's in there, unless there's some differently worded question, it would generally mean adiabatic, which means you would follow that.
And remember, heat is different than temperature.
Heat and temperature are not the same thing. Heat is the energy that changes temperature, essentially.
Just to clarify in terms of using that equation for entropy, can you just reiterate, like, so you plug that ratio into that final one? So
Yeah.
instead of using like TF over T1, you plug in like VI over TI.
So you wouldn't necessarily use it for that equation, it'd be the one above it. The NCV T over T naught. So what essentially is going to be the ratio of the two temperatures and the ratio of the two volumes. If the pressure is constant, those two are going to be equal to each other, the ratios. So that number can be plugged in on both halves. Something also that I just remembered is a lot of time people don't really understand how specific heat works, and this is something that's could be very easily a conceptual question. So the way to think about it, right, is you have your heat is equal to number of moles times specific heat times change in temperature. So if you were to rewrite that and say heat over specific heat is equal to N times change in temperature, what that means is if you have a higher specific heat, it would then take more energy to change the temperature. The higher the specific heat, the more energy required to raise the temperature of a number of moles of a substance. Does that make sense to everyone? Anyone have questions on that? That's something very important to understand conceptually. That'll help you derive a lot of problems and is very likely, I could definitely see that being a conceptual problem. It says there's these two substances with these specific heats, and you add this much energy, which substance is hotter? Yeah. Yeah. The higher the specific heat, the more heat required to raise the temperature of a substance. So like if you were to rearrange the equation, it'd be heat over specific heat is equal to moles times change in temperature, which means that the energy required to raise the temperature of the substance would be related to the specific heat and the number of moles of that substance.
Yeah. Any questions about anything that we've gone over? We could do a couple like examples of homeworks. If that would help, we could just answer questions that y'all have. We have what, like 20 more minutes that we'll be here.
Yep.
So yeah, shoot. Yeah.
What do we know about? What do we need to know about like convection and radiation?
Oh yeah.
Covered in the chapter summaries.
Right. So yeah, with radiation, I don't remember. There wasn't even any homework about that one, was there? And did Professor already talk about it in class?
Nope.
No? Okay. If he didn't talk about it, I don't remember it ever being tested on. So we should be able to not worry about it. The only thing that they might ask about is right here. You see how T is to the fourth in that equation under radiation? Just understand that that's to the fourth. And so if you increase T by 1, you're going to increase your radiation by 4. So it's going to quadruple. That might be a question, but probably not.
Yeah, so this is on page 21. Just good to know the description of what they mean too. I could see him doing, if this is being heated through this mode, is it convection, radiation, or et cetera? So like,
Right.
just good to know that, but
And do we know the differences?